I'm Tom Ballard, the Groundwater guy, and let's launch into the presentation here, along with my co-host Shahab Hashimi. We're going to present on the well health check process for diagnosing well problems today. So let me start off with a question here. Would you drive your car for 300,000 miles and never change the oil? Well, of course not, but oftentimes the way we treat our wells is the most common management method is run to failure. You wouldn't do it with your car. Why would you do it with an asset that is probably running about $1.5 million to $2 million to replace a municipal well these days? Why would you do that? So we're going to talk about the well health check process today that's going to treat the valuable asset that is your well the way it should be treated. So let's dive in here. So the well health check process is part of the systematic well management plan, and it's a 10-step process that manages a well all the way through its life cycle. But really the well health check process focuses on this middle part there that we have outlined on the slide, and that's where you start where the well is kind of it had some life to it. It's starting to run into some problems. And so you're approaching your first well rehabilitation. So you want to start looking at what your specific problems are so you can dial in the well rehabilitation technique that's going to be most appropriate to your well. Now, the important thing to remember here, and what we're going to get at through this whole presentation, is you want to understand what's going on in your well, because well rehabilitation is going to be very specific to the problems that you have in that well. It's not a one-size-fits-all solution. We see a lot of people that approach it that way, and they end up wasting their money on well rehabilitation. You want to tailor your well rehabilitation to the specific problems that your well has. That is what the well health check process is designed to do. So it provides a snapshot of the condition at the well at a specific point in time, and we use it for a couple things. We use it for designing a well rehabilitation program, but we also look at it to track trends when we do this program every year, and we monitor things that are going on in the well. We can understand problems before they become problems, and we can actually optimize our well rehabilitation schedule. So that's what the well health check process gets us. So this is just one example of what's going on down there. You never know from looking at the surface of this particular well, but this is a screened well with a turbine pump in it. So you got the turbine pump bowls there to the right, and the well screen to the left. And believe it or not, this well was rehabilitated not all that long prior to us taking this video. These are calcium carbonate deposits here, and probably some iron mixed in there as well, and they can be deposited fairly quickly here. But you never know that from looking at the surface. It's even amazing that this well is pumping any water at all. Somehow water is finding its way through, but the pump actually failed shortly after we did this video, probably not coming as any surprise if you're looking at this picture. So what are the three common problems that cause well plugging? Number one is chemical or mineral incrustations that are going on in the well. So mineral incrustations generally are going to be due to water quality issues, what the water has in it, but also lower quality screens can be more conducive to mineral incrustations developing. Velocity drop. If your well is designed so the water's coming in too fast to the well, velocity drop at the well can actually contribute to mineral incrustations forming as the velocity drops, and it precipitates out minerals coming into the well. So number two, and probably the biggest factor in well plugging, is going to be biofouling. Biofouling is involved in about 80% of well plugging cases. Generally, it's going to be bacteria like iron and manganese bacteria, related bacteria, but other types of bacteria like Pseudomonas can form biofilms and slimes that can plug up your well as well. So there's a whole host of bacteria that can actually form biofilms on your well that can result in plugging, and it can actually develop very fast. What you're seeing is not the bacteria themselves, but generally what's causing the plugging is going to be the tubercles and the protective slime coating that forms to protect the actual bacteria themselves. That's actually the biofilm. That is not the bacteria themselves. That is a protective coating, and that's generally that gooey peanut butter-like stuff. That's generally what causes the plugging in the wells. So this is actually what a well plugging profile looks like, whether it's mineral incrustations, whether it's biofouling. The majority of what's going on is probably outside your well. So even if you run a camera down the well, you're probably not seeing everything because it's going to be out in the gravel pack, a lot like the iceberg principle. So here we see the well in the middle there. You see the gravel pack where most of the action is happening out into the formation. And what's really important when you do well rehabilitation is to understand not only what you're tackling, the problem you're tackling, but trying to get that energy and any well rehabilitation chemicals out through the screen and into the gravel pack to address the problem there. That's going to be the biggest part of the problem. We often see well rehabilitation fail or not do a sufficiently good job because they shinied up the inside of the well, but they didn't take into account the fact that everything was going on in the gravel pack and not necessarily inside the well. This is a 3D visualization of biofouling. You can see different forms that the biofouling takes extending outside the well. Pay particular attention number 3 here, the concentric detached. That type of thing is what we get when you have an insufficient well rehabilitation. It pushes the bacteria back basically into the formation of the far reaches of the gravel pack, but it doesn't totally address it. So that bacteria, that biofilm can return fairly quickly when you do an incomplete well rehabilitation job. All right, biofilm formation in a well, what's important here is it will grow, it'll colonize on the surface of the casing and the screen. And really when you take a sample of the well water looking at bacteria, it's actually a ratio of 1 planktonic bacteria, that's the free swimming bacteria that will show up in your sample, to 1 million sessile bacteria, that's the bacteria that's actually attached to your well casing. So you got to keep that in mind when you're interpreting your results. Also, the important thing is things like iron and manganese bacteria can form slimes, and things like sulfur-related bacteria can grow underneath those slimes. So you actually get a consortium of bacteria that are actually growing in your well, and that's important to understand. Filter pack clogging is the third method of plugging your wells. This is going to happen with the constant one way of flow of water flowing into your well. You're going to develop these sand bridges. It's going to move sand grains around and get some blockages with sand bridges. But more importantly, the silt and clay particles will move around and they will actually plug up the space in between the grains. It means that water cannot get to the well quite as efficiently as it used to. So you can see that all 3 of these things are going to require different techniques to rehabilitate that well, and I'll talk at the end of this video about what different techniques we use for these different situations. But you can start to see why it's important to understand what your specific problem is so you can get at the well rehabilitation that's going to treat that specific problem. All right, so the well health check process. Number 1, we want to look at biological parameters because they are very important. They really get underplayed. A lot of people don't understand how important they are, but it really is important to understand the biology in your well. A lot of times we're just looking at coliform bacteria because the regulations say we need to, but there's a lot of other stuff going on. There's a lot of other bacteria that are in the well. So we're going to look at things like total bacteria, anaerobic bacteria, iron and sulfate bacteria, those types of things, to really understand what's going on in the well with the bacteria and how it impacts us. So total bacteria counts, we want to look at those because increasing total bacteria counts are going to mean that the environment in the well is conducive to bacterial growth, and eventually you're going to reach levels that aren't healthy. So there's a couple ways to measure that. Heterotrophic plate count only counts aerobic or oxygen-loving bacteria. Adenosine triphosphate, or ATP, measures all the bacteria. We typically will use an ATP count when we're looking at total bacteria counts. The next one we want to look at is anaerobic bacteria. These are bacteria that thrive in oxygen-free environments. These tend to be your bad actor bacteria. So pathogens and sulfur-related bacteria fall in this category. So they can thrive in dead zones in the well. So a high or increasing anaerobic bacteria counts indicate increasing corrosion potential and potential for pathogenic bacteria to be in your well. Sulfur-reducing bacteria is an example of an anaerobic bacteria. So iron-related bacteria, there's a specific category. This picture here is of Gallionella bacteria, which is a prolific slime producer in the wells. It'll produce a lot of biofilm and plug up the wells pretty rapidly. They can grow extremely fast by combining iron in the groundwater with oxygen under aerobic conditions because IRBs are aerobic bacteria, and they can completely clog a well in a relatively short period of time. And that's why we say that probably 80% of well plugging cases are bacteria, and a lot of those are going to be iron-related bacteria. Sulfur-related bacteria, SRBs, they fall into two categories, sulfur oxidizing bacteria and sulfur reducing bacteria. These are anaerobic bacteria. So they will respirate hydrogen sulfide. That's that rotten egg odor you get. That is highly corrosive to your well, and it can eventually punch holes in your casing, erode your screens, and basically produce bad odor in the well. Now, the interesting thing, they're anaerobic bacteria, but they can actually grow under the biofilm produced by the iron-related bacteria where there's no oxygen under there. So you actually get a consortium of bacteria growing. So it can get very complicated. That's why it's important to properly assess the well so you know specifically what you're dealing with there. So I think I've gotten across the importance of microbiology in the well. A lot of people don't appreciate that. I didn't appreciate that as a geologist that is so important, but I've become a lot more versed in microbiology and understanding the microbiology of the wells and how important it is. So, and you can see some of the conditions here. Even some of the iron and manganese incrustations we get on the well are biogenic in origin, so so those bacteria can actually precipitate iron and manganese that'll cause mineral incrustations to develop. And even things like arsenic mobilization in some cases can be caused by certain types of bacteria that are in the well. So this is so bacteria really play a great role in what's going on in the well, and we're finding out more and more all the time how important they are. So it's really important to understand that. The microbiology is a big part of the well health check process. Chemical parameters are something that we look at, and some examples of this are iron and manganese, hardness, alkalinity, total dissolved solids, pH, total cations, ions, and anions, oxidation, reduction potential, and even specific contaminants that we might have in the well. So a lot of these are going to relate to the chemistry of the well that's going to affect the well rehabilitation chemicals you use in the well. So hardness and alkalinity can really affect how much you're going to need of specific acids and the well rehabilitation chemicals to overcome those specific well chemistry issues to actually get at the cleaning process. So we want to look at those. That's part of the well health check process. Iron and manganese are interesting. Iron particularly because iron, we speciate the iron into iron 2 and iron 3. Iron 2 can actually indicate corrosion going on in your well. So levels of iron 2, and especially if they're increasing, indicate ongoing corrosion in the well. Iron 3 is an indicator of you might be facing some treatment difficulties because it can kind of gum up the works in treatment facilities. So it's important to understand your iron levels, and manganese can also support bacteria populations. So you want to monitor the changes over time. Hardness is related to alkalinity and is directly related to calcium and magnesium cation concentrations, and it is what will is important in producing those calcium carbonate mineral incrustations in the well, which is actually the most common type of mineral incrustation that's going on in the well. So potential for incrustations increases if hardness is greater than 250 milligrams per liter, pH is greater than 7.5, and alkalinity is greater than 220 milligrams per liter. So hardness and alkalinity are important. pH, generally pH is going to be stable in a well. If it's changing, that indicates something new is being introduced to the well. It can be the bacteria can actually change the pH or contaminants. So you want to monitor the pH and understand what's going on there. Obviously, for drinking water, you want it to fall within generally that neutral range of 7. But monitoring the pH can tell you if there's things that are changing in your well, and you want to investigate that. Is it contamination, biofouling? Obviously, reduced pH from hydrogen sulfide from sulfate reducing bacteria can be important as well. So pH, monitoring pH, particularly changes, is going to be important. Oxidation reduction potential is going to tell you whether you have anaerobic or oxidizing conditions or reducing or anaerobic conditions. So that's going to tell you what type of bacteria, whether you have corrosion potential, those types of things. Physical parameters. We want to look at the physical parameters as well. Energy usage, sand production, specific capacity, well efficiency, water level trends, pump efficiency. These are all things we're going to monitor that are physical parameters. So for instance, energy usage, well, just measured in gallons per kilowatt hour, very easy measurement. Reduced gallons per kilowatt hour is going to indicate a reduced efficiency of your well, which a lot of times is going to be well plugging, although it could be pump or motor damage. So you got to look at that. There's ways of determining that, looking at wire to water efficiency for the pump. But this is a quick way to get at things. It's real easy to do and see if you have any problems, potential plugging. The sand production should be less than 5 parts per million. We want to measure that. That could indicate damage in the well if you have increased sand production or over pumping, those types of things. So you're going to want to watch that as well. Specific capacity, very good measurement. Real easy to do, is discharge in gallons per minute divided by drawdown in feet. Reduction in specific capacity will indicate plugging in the well. If you don't monitor anything else, you should monitor specific capacity. You're going to want to look at discharge in the well. You're going to want to look at what your pumping water level is and what your non-pumping water level is. That's going to be your drawdown. And as those numbers go down, as the well plugs, that will tell you, that will give you a good indication of when it's time to do well rehabilitation. So interpreting trends, this is one thing to look at here. If you have an aquifer issue, your static water level is going to be declining, your pumping water level is going to be declining, and your production rate is all going to be declining. So that's going to indicate an issue going on with your aquifer. If you have a well issue, your static water level is going to be stable, but your pumping water level and your production rate are going to be declining. And if you have a pump issue, both your static and pumping water levels are going to be stable, but your production rate is going to be declining. So that's kind of a quick and dirty cheat sheet for determining where to look for that specific problem. All right, operational data. This is the fourth area we want to look at. That's going to be kind of a hodgepodge of things. Well videos, obviously very important. We recommend every time you pull the pump, you do a well video. Well construction information, driller's logs, e-logs, well operational history, well rehabilitation records, analytical data, maintenance records, pump check data. This can all help us diagnose specific problems that you see from the chemical and the biological parameters, what's going on with the well. For instance, driller's logs are one of the first places I go. You can usually identify if you have a seal problem, a well construction problem. We've solved many problems just by looking at the driller's log and saw what the problem was, and we were able to kind of figure out how to fix it just from doing that. So that's going to be your friend. This data is, don't pass that by. You want to look at it. So, okay, interpreting the data. Key performance indicators are what we use, KPIs. They're a powerful tool to indicate the health of a water supply well and determine the optimal schedule for rehabilitation. So we look at KPI changes over time. Tracking trends are going to be very important. This chart here shows basically declines in specific capacity over time. So you have specific capacity on the y-axis, and on the x-axis you have time. And you can see the blue graph there. That's declining specific capacity over time. You get down to a certain level. The star is where they rehabilitate the well. They bring the production back, and then the cycle starts over again, because well rehabilitation is not a one-shot deal. And so you can see what the short-term trend would be if you just did run to failure and you let that well fail. You can see that that capacity is going to go to zero specific capacity, relatively short period of time. Whereas you look at the longer-term trend, where you're doing regular well rehabilitation, as it's indicated, you're going to see a life on that well that's 4 or 5 times what you get with the run to failure model. And with municipal wells costing in the $1.5 to $2 million range, that is an asset management technique you definitely want to pay attention to. So you want to track these things, you want to graph them up, and you want to keep track of them in a KPI dashboard. A lot of people just take their analytical data and all this stuff they collect, they look at it, they throw it in a file and never look at it again. You don't want to do that. If you're tracking trends properly, you're going to put that on a dashboard, you're going to graph it up, you're going to want to look at what the trends tell you, and you're going to get an idea of when the optimal time is to do well rehabilitation. Let's face it, well, rehabilitation is pretty expensive. You don't want to do it too soon, but you don't want to do it too late. The well health check process is going to allow you to optimize that. So what do these KPIs look like? So we have them in our 3 areas here, the biological parameters. You can see here we have a green zone, a yellow zone, and a red zone. Obviously, if you're getting into the red zone on these parameters, you're going to want to look at that and start scheduling up a well rehabilitation pretty quickly. If you're in the yellow zone, you have a little bit of time, but you definitely want to start getting that on the books and budgeting for that. If you're in the green zone, generally you're going to be okay. So these are the parameters we use for the KPIs to track these parameters. Chemical parameters, same type of thing, green, yellow, red. Now, some people will assign numeric scores to this, and that works too. And you understand what your number ranges are. It gets you to kind of the same area. I like the green, yellow, red, because it really jumps out at you, and rather than the numbers don't always jump out at you. So if you got a lot of stuff in the red zone, then you're really going to want to pay attention to that. And you can actually you can take your KPI dashboard and program it up to change colors. So when you start seeing a lot of stuff in the red zone lighten up, then you're going to want to look at that. So these are the parameters for chemical, and we even got any specific contaminants you're dealing with, arsenic or nitrates, those types of things. We want to look at those relative to the MCL. Everything else, we're kind of looking at specific ranges here on whether they're green, yellow, or red. And finally, we have our physical parameters. We're more looking at these in terms of decline, except for sand production. And so percentage decline. So take the gallons per kilowatt hour, 5%, less than 5%, you're in the green, 5 to 15%, you're in the yellow, and greater than 15% decline means you have some substantial plugging going on. So you're in the red zone there. All right, so you're going to look at all these things. You're going to look at the parameters. You're going to look, green, yellow, red, and you're going to come up with recommendations for your well rehabilitation based on what problems you have and make those specific to the well. So you're going to basically come up with a recipe that you're going to give to the well rehab contractor. And I tend to prefer well rehab contractors that specialize in well rehab as opposed to drillers that just kind of do it as a sideline. You're going to get much better results. But you're going to want to have something that's specific to the problem you have identified in the well. You're going to make those recommendations, and that's the course you're going to plot. So how does the well rehabilitation approaches look for each problem we have? So you can see here it's markedly different. So that's why understanding what the problem is, then getting to the well rehabilitation that's specific to that problem is going to be important. So mineral incrustation, you're going to go in something with a hydropulse or shock treatment. You're going to then go in and swab the well to kind of break stuff up. You're going to go in with a mineral acid, something like hydrochloric acid, and then you're going to swab that in, and then you're going to do probably another swab and then a flush and get rid of that material and clean up the well. For a biofilm, something like a shock treatment is not going to work because you're dealing with soft biomass. So you're going to want to go in with a brush and brush that and break it up. And then you're going to go in with a flush to get all that stuff out. And then you're going to go in with an organic acid. And organic acid is more specific to biofilm, and it'll be a lot more effective than a mineral acid. So once again, you can see why it's important that you properly diagnose what the problem is. And then a swab and a flush to clean things out. Silt and clay plugging, you're going to go in and you're going to brush the well to clean the screens out so you can get access. And then it's going to be a lot of swabbing and flushing and trying to break up that the silt and clay that's been plugged up in there and break up those sand bridges. And then finally, you're going to flush. So that is our presentation today. I will be happy to entertain questions.